All right. So yesterday we wrapped up Unit 2 with our test. A lot of things linear equations. We did graphing, we wrote their equations, we manipulated those equations, we even talked about parallel and perpendicular lines, which was really kind of a nice segue into this unit, which is our shortest unit by far, where we do in fact deal with two lines at a time. So parallel and perpendicular lines were two very uniquely related lines. And we're going to look at all the other lines, and what they do and why they're so interesting to make those comparisons. So this unit is all things systems of linear equations, and we'll also have a small snippet where we do a system of inequalities as well. So half of what we do today is actually review, because half of what we do today is graphing. The only difference is instead of graphing just one line on the coordinate plane, we're going to go back and graph a second line over top. And our end goal is to figure out, okay, where do these intersect? That is going to be kind of our main focus here today. So again, if you want to read some of this, it goes into a little bit more detail. We are in total going to cover 3 different methods for solving these systems of equations. We're going to start with graphing, just because it's a very visual process. We get to literally see exactly what point the two lines share. And then we're going to introduce 2 slightly newer topics, newer methods. We'll look at substitution, which is another thing we're going to cover today. And then next Tuesday, when we come back from our long weekend, we'll look at elimination as well. Now, to say that one of these methods is better than all the others, it really depends on your personal preference, how the system of equations is given to you, and things like that. I will say typically graphing is the least effective, only because, and we saw this when we started our unit on graphing linear equations, we don't always know if our little window, that is our coordinate plane, we don't know where it's going to fit in the big picture. So because graphing sometimes is kind of up in the air and we don't know even if they're going to intersect where we can see it, it's usually the last thing we rely on. Substitution and elimination are going to be the big ones we focus on a lot. So like I said, first half of our notes today is going to feel a lot like review. In fact, it's some of the skills that you just tested on as of yesterday. So like I said, there kind of summarizes, it is a great way to visualize. It is the least accurate, least efficient method we have, especially when sometimes, as we know, 2 lines could intersect between clear coordinates and could cross at an ordered pair like -1.739, comma 3.564. Visually, we won't be able to distinguish that. Algebraically, we'll have to come back and look at those. So to solve these systems of equations by graphing, we're going to graph each line as if we were graphing a line from the last unit. And if you recall, ideally, we prefer to graph things from slope-intercept form. So just a quick recall there for you. Slope-intercept form, of course, is y equals mx plus b. From that, the y-intercept kind of gives us our starting point. The slope walks us in the direction that the line's traveling, finding additional points along the way. What we're looking for is what the 2 lines have in common. And the only thing that lines could have in common is that they share one of their points. So I know it's bolded already, but what we're essentially looking for is where they share a point by intersecting. We're looking for the point where they intersect. So there's a nice summary there for you. Graph the lines, write the ordered pair for the point of intersection. If you were to boil it down into one simple statement, that is what our goal is for these problems. Now, right off the bat, what's my biggest complaint currently?
Neither of them are in slope-intercept form?
Neither of them are in slope-intercept form. And how can you say that? Why do you know?
Y is not alone on one side.
Right. So neither of the y's are by themselves. So we can't quite graph them yet. We have a little bit of work to do for each of these. So what I'm going to do, so I have some space here, I'm going to write down the first one off to the right here. 1x minus 3y equals -6. Put my little guideline in here so we can keep ourselves oriented. What would you move first to get that y by itself?
1x.
That 1x, because remember, the y is on the left, that's the side we're focusing on. So I'm going to use a -1x to make that disappear, making sure to do it on both sides.
And the 1x on the left side would cancel out,
Mm-hmm.
and then it would be -1x,
Oh.
well, -3.
-3y.
Equals -1x minus 6,
And why didn't you combine those?
because they're not like terms.
So anytime you're writing things over there, if they are not like terms, don't try to force them together. If they're not like terms, just bring them on down. Just make sure you bring their signs with them. If they're
And then
negative,
you
they
would
stay
divide
negative.
Everything by -3. The
Okay.
-3y cancels out, which leaves you with
So hold on, you're talking way faster than I can relay to the people on the other line. So you're moving the -3 and you said you're dividing everything by that -3, which sounds good. I understand sometimes we get on such a roll, we don't want to stop. So you said on the left, it is going to simplify to a +1, which leaves the y by itself.
1/3 x.
You said a 1/3 x, and then Marissa, I see your question. I'll come right back to that here in just a second. And then you said
Plus 2.
a -6 divided by -3 gives us a +2. So that top equation is now in slope-intercept form, which we'll talk about here in just a second. Marissa's question, though, she asked, so if we do -1 on each side, do we just bring that down because we can't combine and cancel on the right side? So I'm going to slightly address the first part of your question real quick. On the left-hand side, we're not just subtracting or using a -1. Sounds like I'm nitpicking, but we are doing a -1x. So we don't want just the 1 to disappear. We want that whole term to disappear, which is why we're using a -1x. That is now gone. 1x minus 1x is technically 0x, but zeros hide. On the right-hand side, to keep it balanced, a -1x on the left, we need a -1x on the right. I've said it a few times before, don't get lazy on me at this point. If you're subtracting a 1x, I've had some students just put -1. And if you just put a -1 here, they would look like terms. You're not just moving 1, you're moving the 1x, and which is why we couldn't do anything more. We just dropped them on down. So I dropped the -1x down, dropped the -6 down beside it. Marissa, I hope I didn't dance around your question and not hit the mark. Did that help clarify anything for you, or? Okay, good. She says she's good. Hopefully she's really good, because sometimes students are like, I don't want to ask a question again. Challenge me. Sometimes I get stuck in my own head and I don't think I'm answering the question, and I answer another question that was never asked. So good. So we're here at slope-intercept form. From that, we can pull the 2 key pieces of information we need to graph this line successfully, which is our y-intercept, in this case being I tricked you. I switched the order in which I asked for them.
2.
Is the 2. And the slope, which is 1/3. So with that information, if I slide over here to where I can see my coordinate plane, that y-intercept, Again, reminder, this is the point where our line, or this line, crosses the y-axis. I'm going to find positive 2. And a slope of 1/3 has me traveling where from that y-intercept? Up 1. To the right, 1, 2, 3. If you're ever not sure which direction, left versus right, up versus down, check the signs. Positive directions are up and right. Negative directions are down or left. But this case, positive 1 over positive 3 has me going up 1, right 3. And just so I have an extra point to see it, I'm also going to do the opposite. Down 1, left 3, which lands me right here.
And the fractions are rise over run. Right?
Fractions give us our rise over our run. The numerator of our slope tells us the vertical change that we must travel. And then the denominator of our slope tells us the horizontal change, the left versus the right.
The numerator is vertical and denominator is horizontal.
Yes.
Sorry, I'm trying to rewrite some of this now.
No, you're fine. Typically, when I refer to slope, I just say rise over run. But if you want to add that extra detail, sometimes rise over run is like, what? It's like you just added an extra layer of confusion.
I'm doing both vertical / rise.
Nope, you're good. There's actually lots of ways to describe slope. I'm going to get slightly off track here, but there is, I think the technical definition is the change in y over the change in x. If you think about it, y would be our vertical change, x would be our horizontal change. And if you get into more advanced mathematics, not to scare you too much, but they use the Greek alphabet, particularly the letter delta. They do delta y over delta x. Delta typically represents the change in that variable. Now, if you're like, I don't like it, that's okay. I don't think I started saying that until like pre-calculus or calculus, which fortunately you don't need those classes for your high school diploma, depending on what path you take. Beyond high school though, there's a chance it may come up, maybe in statistics, maybe, I don't know. So bringing it back, we have some points there for our line. So I grab my straight edge, draw in that line just so we can see where it's traveling. And at this point, normally we'd celebrate because we'd be done. There's only one line. That's all we needed. However, this is a system of equations, so we have 2 of them. So we're halfway there. So I slide back over here, take a look at my second equation, 2x plus 3y equals -3. Copy that down, put in my little guideline there. We repeat the same process we just used. Also not in slope intercept form, so we're getting that y by itself. What would you suggest we do first?
Subtract the 2x from both sides.
Subtract the 2x from both sides, okay. So minus 2x on both sides. Let's see what that does for us here. On the left, 2x minus 2x is 0x, or just 0, which is why we're allowed to hide it now, leaving just 3y on the left-hand side. Drop down my equal sign. -3 and -2x, are they like terms?
No.
They are not, so we just drop them down without messing with them. So I like to bring down the x term first, just so it feels more like that y equals mx plus b format that we're typically more comfortable with. What still needs to move?
3.
The 3 off of the y. You're looking at the right place. How are you going to split that 3 off the y?
You're going to divide it by all sides.
Divide everything by that 3. So Marissa, not to count her out, she's over here in the chat. She also drew attention to the 3 as well. So we're going to divide every single term by this 3, watching our division as we go through this process. On the left, 3 divided by 3. It's a +1. We like those because they hide also, at least when it comes to multiplication. -2x divided by 3. So remember, slopes typically are fractions, so don't panic there. Just make sure it is simplified. So double negatives will become positive, which doesn't affect us here. Does 2/3 simplify? No. So it looks like it's going to stay a negative 2/3 x. And then what about negative 3 divided by 3?
-1.
Is a -1. So far, so good. Traveling right down the right path as before. I'm going to use my little neat tool here to cheat. Ta-da. So with it in slope-intercept form, what's my y-intercept?
-1.
A -1. And my slope
-2/3.
is a -2/3. Again, we're using the same coordinate plane, so we already have a line there. That's okay. We're just going to kind of graph around it here as needed. So our second line has a y-intercept at -1. So we'll find that on our y-axis and put our first point for this line. And it has a slope of -2/3. So where's that sending me? Down 2 units. So 1, 2.
To the right 3.
To the right, 1, 2, 3. Now, if I were to do the opposite, this is going to be where some of the magic happens. I would also have gone up 1, 2, but then to the left, 1, 2, 3. But I already see a point there, which is going to be very useful here in just a moment. Because we graphed it with the other line. We now have 2 lines on the same coordinate plane. And what do they happen to be doing?
Intersecting.
They're intersecting. And could you tell me specifically where they are intersecting?
Or -3.
Ooh, careful. You have the right coordinates, but the x coordinate always comes first.
So -3/1.
It would be -3 for the x coordinate, 1 for the y coordinate.
And x always comes first. On
X
the
coordinate, and if you want, I can jot this down here. X always comes before y. It's always very alphabetical with ordered pairs. So while some of you are still jotting this down, I've got a few comments here. Oh, I did. Now I'm off on the spot. I forget what I was going to say. Oh, shoot. It felt important at the moment. Oh, yeah. So one of the recommendations I would give you, again, I can't twist your arm and make you do it my way, nor do I want to. But because you are dealing with 2 separate equations, and each of those equations both have a y-intercept and a slope to deal with, I would recommend doing what we just did together. Work with just one of them all the way through. Get it in slope-intercept form, identify the 2 parts you need, get it on the graph. Because what I have seen before in the past, I'm also guilty of it, is you're trying to do the 2 problems through at the same time. So you get this one in slope-intercept form, you get this other one in slope-intercept form, and then you go and you write the y-intercept and the slope, the y-intercept and the slope, and then you go to try to graph both of them at the same time. And can you guess what the most common mistake is in that scenario? I've seen students take the y-intercept from one equation, the slope from the other equation, and use them together as if they were from the same line. So what happens is you get this really weird hybrid of information, and it obviously is going to affect your overall graph. So what I would suggest is don't try to juggle too much at once. When you start with an equation, see it through all the way to getting it on the coordinate plane before going back and addressing the second one. Hopefully then you'll avoid trying to juggle too much and accidentally scrambling your information. Because as I always repeat annoyingly, organization is very important here. Detail is very important. Don't rush through these. Take a little pride in your work. Make it look as clean as you can, because it's going to make what seems like a difficult problem feel all the more easy. or at least easier. Easy is relative to each individual person. So how do you guys feel about this? Can you graph two lines?
So real quick, the
Yeah.
solution to both of these will be where the two lines intersect at -3, 1.
So good question.
Because I was about to ask, like, when two lines intersect, do they have something special that they're called, like when you have a Y or an X intersect?
So I'm going to go back to your question first. You said, in this case, is it the solution for both? No. That question technically doesn't apply here because a system of equations is not two separate problems. Yes, it has two lines involved, but it is seen as one individual problem.
Okay.
So the solution to this system, which is these two equations, is that -3, 1 that we found. Now, sometimes in, say, math textbooks or assignments, sometimes you'll see systems written with a little brace out to the side saying that these are two parts of the same one problem.
So it's not two equations with one solution. It's one problem that's built from two equations.
That's a good way of putting it. So it's, yeah, it's not two separate there's two separate problems. It is one problem, one solution. Now, just to tie it all the way back and bring it full circle, what that solution means, if I wanted to see the algebra behind it, because we're looking at it very visually right now, but if I wanted to see the algebra behind it, if I were to take this -3 and put it in the x of my first equation and put this 1 in the y of my first equation, I would have -3 minus 3 times 1, which is -3. -3 minus 3 would give me -6. I would end up with a true statement. That's good. It should be, because that point is on that line. But if I were to do the same thing with the second equation, take this -3, drop it in for this x right here, take this 1, drop it in for the y, I would have what? 2 times -3, which is -6. 3 times 1, which is 3. -6 plus 3 is -3. It works for both. And the reason it works for both is because that point, that -3, 1, that we visually spotted was on both of our lines. And because it was on both of our lines, and it was the point that they shared, that is what deems it as the solution to this system of equations. Now, my wife tells me that I'm very long-winded, but sometimes it's just because I get so excited, and I think there's such a big picture here. And we kind of just have to take a moment to appreciate it. These systems of equations, why they play such a keen role in what we do. The example I like to use is in business. If I want to start a new business, and I boiled it down to its two most basic components, I'm doing two things. I'm spending money, I'm earning money. But what makes it a profitable business is when at some point, eventually, hopefully down the road, hopefully soon, the money that I'm spending becomes less than the money that I'm earning. Because if you know, unless you've acquired a large inheritance, to open a new business, you typically have to borrow money, which means you start off in debt. But a good business, and I think the average is like 3-ish years before a business can sustain itself, is when your expenses, which is typically a linear equation, and your earnings, which is a slightly steeper, or should be a steeper linear equation, is when they meet. That point, which would be the solution, is called the break-even point. The point where your business has now paid off its prior debt, and the money it's earning can continue to sustain the money you're spending. Now, we could spend the whole day talking about this. I find it interesting. Not everybody does. But this has a lot of real world implications that would allow someone who's considering opening a new business, check to see, are my prices, on track? The resources I'm acquiring, can I afford to buy them at this price? And it can kind of allow you to make future projections to see, okay, how long before this business hopefully becomes profitable.
I was an assistant manager at a pawn shop. I can vouch for on that. It's overwhelming when you don't know what you're doing. You start looking at all those numbers and you're like,
Yep.
you think books, you think, oh, you know, a cost and a expense, you know, a profit and expense column. No, not quite.
Yeah, you have to really balance those numbers
Yeah.
carefully.
And there's a lot more numbers than just that too.
Yeah, so this is kind of an oversimplification of that. There's typically more variables involved, but at its very basic, understanding, you're trying to make the two lines, eventually the good line, the green line, grow faster than the red line. Again, oversimplifying it a little bit, but if that is something that interests you, you will see a lot more of systems of equations in your future. Now, as always, we have those gosh darn special cases that like to rear their head. One of them is actually a special case we've come across before. It just has different implications now. And the other one is, it's kind of deceiving when you look at it at first. So the first one I want to look at, really there's nothing we need to do here, we're just going to talk about it, is the possibility of getting a system of equations that produces no solution. Well, what can you tell me? What do you see on this graph? What are these?
Parallel lines.
They're parallel lines, which, as the notes there say, do what? They never intersect. Well, think about it. If our solution comes from the point of intersection and parallel lines never intersect, kind of makes sense that there would be no solution. No intersection point, no solution. So parallel lines, regardless of where they're at on the graph, all parallel lines will produce a system that has no solution. Now, if this was our business model, that's not good, because obviously we want that intersection point to where we can get ahead. But in some scenarios, our lines turn out parallel. Bonus question, to throw it back to just our test yesterday, if I hadn't given you this graph and I had just given you this system of equations here, y equals negative x minus 1 and y equals negative x minus 3, would you know that this is no solution?
Yes,
How would you know?
because -3 and -1 are on different points of each other.
Right, but those are y-intercepts. Of course they're going to intersect at different points, typically.
The slopes are the same?
The slopes are the same. What does that mean?
That they're parallel?
They are parallel, yeah. If you recall back to the last lesson from our last unit, we knew we had parallel lines, or at least we used the fact that parallel lines have the same slope in order to write secondary equations. But that was a fact that we believed and we used to our advantage. That fact doesn't cease to exist. Parallel lines are parallel because their slopes are the same. And both of these have a slope of -1.
So I was just about to ask, it's like,
So we don't see it exactly, but it's in there, it's hiding. The slopes are exactly the same.
So you can infer a no solution when the slopes are the same.
Now, you can only come to that deduction if your equations are in what form?
Slope intercept form.
They would still have to be in slope-intercept form to come to that conclusion. But yeah, you could actually save yourself some work there. Now, I think there is one on the assignment today that has no solution in the graphing section. I just for the sake of practice, I still ask that you graph them. So you'll know they're parallel, but when you go to graph them, they should visually be parallel. But yeah, so good job, Tiara. Once you identify your slopes are the same, you already know kind of what path you're on. The second special case is infinitely many solutions. Now, if you notice, well, actually, let me ask, what do you notice about the two equations I've given you here?
They're the same.
Exactly the same?
They have the same y-intercept?
They have the same y-intercept and the same slope. They're 100% identical. Well, as we know from graphing lines, each unique linear equation produces a unique line. Therefore, if you have two of the same equation, in essence, you have two of the same line. Well, as the notes there kind of suggest, and I'm going to kind of, I don't know if this is going to translate well on this on the image. Let me increase my pen size maybe. What is happening, though we can't see it, is on top of this line, there is a second line going, ooh, I hate that. Going exactly the same direction, exactly through all the same exact points, which means every point that one line goes through, so does the other. So how many times are they intersecting? Infinitely many, because there's infinitely many points on any one line. And if these two lines are going through all the same points, there are infinitely many points that would be considered the solution. So we can't even list them because the list would go on forever. Now, does that mean that any old point would be a solution?
No.
No. Why not? Give me an example of a point that's not a solution here.
+3, +3 and 0.
+3, 0, which would be right here. Yep, that's not a solution because it's not on either line. In fact, any point over here, and remember this graph continues to go on forever and ever and ever in both of these directions. There are also still infinitely many points that are not solutions. So sometimes students think infinitely many, that means everything's a solution. No, there's different parts of infinity, which is kind of hard to imagine at this level, but know that any point on these lines would count. So I don't know, 1, 2 would be a solution. 2, 5 would be a solution. -1, -4 would be a solution. Every point in between would be a solution.
So basically what you mean by infinitely, since the line is infinite, there is an infinite number of solutions along the line.
Along the line, yes. Good. So what's nice about doing this graphically is that we can visibly see beyond any doubt that, oh, parallel lines, of course there's no solution. They're not intersecting ever. Or, oh, two of the same line. They're right on top of each other. Of course, they're always intersecting. Of course, there's infinitely many. So visibly, it makes a bit more sense. But as I've said a few times now, graphing isn't the most efficient. It's not always the most accurate. So knowing that those special cases are in there, we're going to have to keep those in the back of our mind to figure out, okay, as we learn these other methods, how are we going to spot that we're dealing with a special case? Because if you're not graphing it, you're not going to see it, at least not with your eyes. Well, that's weird to say. Obviously, you do algebra with your eyes, but you're not going to see it on a graph. So here comes our second method for today. Substitution. So when graphing lets us down, because maybe they intersect at an ordered pair like 107, 263. I've never given you a graph big enough to do that. So when graphing kind of lets us down, we can always fall back to one of these other two methods. Today's method includes substitution. So I'm going to read through these steps here real quick, but I'm going to tell you, I'm going to comfort you real quick to let you know that some of them don't make sense until you're in the heat of the moment, until you're using them. So bear with me. If they don't sink in first, that's okay. So the first thing we're going to do using substitution is we're going to get one of the variables. Does it say which? No, it doesn't say which. From one of the equations. Does it say which? Nope. So literally any variable from any equation by itself, if necessary. Sometimes we're lucky, sometimes things work out. But once that variable from that equation is by itself, we're going to box it in and remember what it is set equal to. Thank you, Chris. that box is going to serve a purpose later on. In fact, in the second step. Once you have that box, you're going to take it and substitute it in for, excuse me, oh, I lost my train of thought. You're going to substitute everything that's inside the box into the variable that it is set equal to. So if you have x equals a bunch of things, you're going to replace the x. If you have y equals a bunch of things, you're going to replace the y. There is a hint. That box is containing multiple pieces of information. When we go to do a substitution, the box is going to be a bit cumbersome to carry through our process. So I recommend using parentheses to keep your boxed items grouped together. And in fact, that's going to help us in the following steps because we know what to do with parentheses, hopefully. So once you've made that substitution, you're going to have a really new hybridized equation that I want you to solve. And you're going to notice that that new equation has only one variable remaining. Once you get that solution, step 4 says to use that variable solution that you got in step 3 and take it all the way back to step 1 where you have that box and do another substitution. By the end of the story, you should have a value for x and a value for y, which will allow you in step 5 to write your final solution as an ordered pair. Now, some of that might have been right over our heads. Wait till you see it in action. So you guys have those steps there in front of you. I'm going to grab myself an extra copy so I can read them out loud as we go through it. So step 1, get one of the variables from one of the equations by itself if necessary. So that's the first half of step 1. What are your thoughts on that?
The x is by itself?
The x is by itself where?
In the top equation?
So part of step 1's already seems to be done for us.
I got a quick question.
Yeah.
Your old recommendation of moving the smaller of the two, does this apply here as well? Since, like she said, the x is already kind of by itself, so that's technically the smaller of the two.
So the moving the smaller of the two typically applies when you're solving just a single equation.
Okay.
Now that we have 2 equations in there, it gets a little bit more involved, which is why we're learning this new method.
Gotcha.
So I can actually take a quick step back. So Tira, hold that thought. We're going to use that here in just a moment. But if I take a step back, every equation we've solved before today usually only had one variable in it, just an a or just an x or just a y. Now it may have been scattered through the whole equation, but we did our parentheses, we combined like terms, we got that variable to one side, and then we solved for it. Now, however, we have 2 different variables. And the problem with that is if you have 2 unique variables, the only way you can successfully solve for those variables is if you have at least 2 unique equations. So not to spoil too much of the surprise, when you move on to Algebra 2, you're going to still use substitution and elimination, but she's going to introduce lines that exist in 3-dimensional space with 3 variables. If you have 3 unique variables, you'll then be dealing with 3 equations at a time. Now, don't panic, because everything I teach you today and then next week throughout this unit are the same exact skills you can reapply in Algebra 2. So I'm laying the foundation for you now so that it's less of a shock when you get to Andrea. But yeah, so going back, moving the smaller of the 2 typically applied back when we had just a single variable equation, just one equation. Now that we have 2 equations, 2 variables to kind of track, we're using this adjusted list of steps, which here's the thing, I don't even expect you to memorize these. I will give you this list. Today, you're going to have this list as you work through the assignment. If you can follow a recipe in the kitchen, you should be able to go through step 1 through 5 for every problem today using substitution. So eventually it's just going to become a habit without you realizing it. So let me bring it back real quick. Tira said that the x is already by itself in the top equation. So according to step 1, it said if necessary, and it sounds like we don't have to really do anything to make that happen. So I'm excited there, but it does then continue to say that we need to box in what it is set equal to. So in the top equation, what is x set equal to?
1.
There's a 1 beside the x, but if you literally read that equation,
It's equal to 3y minus 6.
x equals 3y minus 6. That is going to be what I box in. So according to that top equation, x, sometimes we swap out the word equal, x is 3y minus 6. So I go into step 2. It says, substitute everything from the box, which in this case is 3y minus 6, into the appropriate variable of the other equation. So now I remember I have a second equation, and there is an x in that equation as well. Well, according to the first equation, x is the same as 3y minus 6. So I'm going to take everything in that box and bring it down here and drop it right where the x is. I'm not going to touch anything else. The only thing being replaced is the x. So this is where that hint comes into play. We're going to use parentheses to keep our boxed items grouped together. So what I'm essentially doing is I'm going to rewrite the second equation, but as soon as I get to the x, instead of writing x, I'm going to write my 3y minus 6. Now, for the sake of space, let me think here. I'm going to write it over here to the right. I think this will give me enough room. So the bottom equation is 2 times x, but instead of x, in parentheses, I'm going to write 3y minus 6 plus 3y equals negative 3. I'm going to preemptively put in my little guideline here. So in essence, what I have done is I wrote the second equation, 2x, which is this big mess now, plus 3y equals negative 3. The only thing that has changed is where the x was originally is the information we took from our other equation. Now, let's pretend that this was just unit 1 again. If this was the equation I gave you, where are your instincts drawing you? To those parentheses. And your instincts are telling you to do what with those parentheses? Distribute the 2. Let's see where this takes me. 2 times 3y is going to give me 6y. 2 times negative 6 is going to give me a negative 12. The 3y was not part of the parentheses, so I'll just bring it on down. Same as the equal sign. Same as the negative 3 from the other side. So far, so good. Now, after parentheses, what did we typically look for next?
Like terms.
Like terms. Do we have like terms?
Yes.
Where?
On the left side, 6y and the right.
6y and the 3y. So remember, like terms, because they're already on the same side, I don't want to do any opposite sides. No fancy moves here. Just combine them as they are. So what does 6y and 3y make? 9y. Now, I didn't touch that negative 12, so I still need it. So I'm bringing it on down along with my equal sign, along with my negative 3. Now, where are your instincts pointing you?
Add the negative 12 to both sides
Add the negative 12 to both sides, and why? What's your goal? What are you working towards?
to get y by itself.
Get that y by itself. So you said, did you say add 12 to both sides?
Yes.
Okay. So on the left, the negative 12 plus 12 is 0, which is gone. Still leaving me with the 9y.
Are we on the back?
Yep, we are. On the right-hand side, we have negative 3 plus 12. Positive 9. Addition and subtraction, signs are different. Find the difference, keep the sign of the largest. I'm sure someone out there has created a quippy little way to remember that, who's more creative than me. I'm almost there, or at least I feel like I'm almost there. What's left to do? Divide by 9. Again, doing it from both sides. On the left, 9 divided by 9 is 1, which allows me to hide it next to that y. On the right, 9 divided by 9, still 1, but that's the one I need to actually see, because now I have some new information here. I now know, according to the algebra that we just did, that y is 1. And although I didn't read it to you, we just did step 3. Step 3 was solve that new equation, which was right here that we wrote, for the remaining variable. And it just so happened that the remaining variable this time was y. It may not always be y. This time it was. So then I move on to step 4. Step 4 reads that we're going to use the variable solution from step 3, which we just found to be y is 1, to substitute that new information back into the box that we used earlier to solve for the second variable. Because what do we know about ordered pairs? What do they always need to have?
An X and a Y.
An X and a Y. We just have Y. We need to find the X that goes with it. So I'm going to use that box. Get real fancy with my notes here. I'm going to take this equation from earlier and bring it all the way over here and rewrite it. So our top equation was x equals 3y minus 6. Put my little guideline in here, always trying to stay organized. But now, some new information we've been given is that y, or at least the y that we're looking for, is 1. So I can take that top equation, rewrite it, but when I get to the y, what am I going to put in its place? A 1. Well, the x is already by itself. That's nice. That's what I'm still looking for. But on the right-hand side, we have some cleaning up to do. Would you do that multiplication first?
Yes.
Yeah? Okay. So 3 times 1 is 3.
Minus 6 and x equals negative 3.
3 minus 6 gives me a negative 3.
And the solution would be negative 3, 1.
Okay, so that was, we just finished step 4. Step 5 says, write your final solution as an ordered pair. Now you said negative 3, 1. Why is that? We found the 1 first. Shouldn't we write that first?
No,
Why not?
because the x comes first because you're moving along the x-axis first.
So as with any ordered pair, x always comes first. So for our solution is negative 3, 1.
But that was a good way to explain it.
So I didn't even see the graph, but I can tell you now through this process, if I were to graph these two lines, I know exactly where they're intersecting without ever even graphing them. I know exactly where they're intersecting. No guesswork. Now, spoiler, we actually already graphed those two lines previously. This bottom equation is exactly the same. All I did with the top equation was add the 3y to the other side. We've actually already solved this system twice now. So the reason why I did this in the notes is because I wanted to prove to you that you can solve the same system of equations by graphing, because look at the solution we got, it was -3, 1, or through this new process called substitution. Now, substitution, it'll take a little bit of practice, but if you have those steps next to you and you read through step 1, 2, 3, 4, 5, as you work your way through it, but let the problem fall into place for you. So as long as you accomplish each step in the appropriate order, it should all fall into place. Now, if it doesn't, we get lost along the way. That's why I try to give you as much work time as possible, because that's where I say, you forgot a negative sign. Usually that's what I say, because usually it's just a sign issue, or, you distributed, but you only multiplied the first term, not the second term. Usually it's a little mistake, because people usually pick up this process fairly well, so long as you follow those instructions that I've given to you. Now, inevitably, I always can see the students that are going to struggle more is usually the ones who put their notes away and then try to do the assignment. No need to be a show-off. Those notes are there to help you instill that routine to become more natural. Now, what about those special cases? Visibly, on a coordinate plane, we could see, those lines never intersect, or those lines are right on top of each other. What are we going to do with substitution? If I'm not giving you a graph and I'm not asking you to graph them, how do I know it's no solution versus infinitely many solutions? Because so far, this process worked out very nicely in this problem. It gave us that X and Y that we're looking for.
Wouldn't you have to first have them both in slope intercept form to be able to see?
So I like that. I like where your head's at. Yes and no. So Jordan said, why not get them in slope intercept form? Because we know that if their slopes are the same and their y-intercepts are different, they must be parallel. If both equations are the same, well, then they must be the same line. Now, here's the thing, though. I've obviously told you that these systems are special cases, but if I just said, here's a system of equations, and I said, solve it using substitution, would you want to first put them both in slope intercept form before you try to use substitution, or would you just want to jump into it and try to solve it?
I'm trying to solve it a bit easier.
Yeah, I would just try to solve it. I don't want to try to do extra stuff, because I usually only put things in slope intercept form if I'm planning on graphing them. I don't plan on graphing this one, so I'm going to think, you know what, I'm just going to assume it's just a regular old system of equations, and I'm just going to try to solve it. Now, that's exactly what I'm going to suggest we do there. And it also gives us a chance to practice some of our steps.
The substitution one?
Yep, the substitution steps. So bear with me for a moment. Yep, I know this, the surprise is ruined. I know we know this is no solution, but let's pretend we don't know. Let's say that I just said, solve this. We go, okay, let's do substitution. Step 1, get one of the variables from one of the equations by itself if necessary.
So I'm finding it easier just to imagine that we're going to do the 5x plus 1, box that in, and then plug it into y on top.
Okay, why is that drawing your attention? How do you know that that's what we box in?
Because y is already on one side by itself on the bottom equation.
Perfect. Let's run with that. The bottom equation already has y by itself, so half of step 1 is already done for us. All that we need to do for the rest of step 1 is to box in what that y is equal to.
And just to clarify, if we had two of these that weren't like that, we'd have to get one of them like that and then do the box in and substitute.
Correct. So if they were both in that standard form I kind of threw at you the other day, and I told you it's mostly useless. If they both are in that form where the variables are scrambled in for both of them, you'd have a little bit of extra work to do on step 1. Here's the good news, though. I don't give you any of those, because on Tuesday next week, when we come back from our weekend, I'm going to show you a second method that would supersede this process if it wasn't already set up favoring substitution. This one's already favoring it because one of the variables is already by itself. The elimination method I'll show you later works if this doesn't work already. So yes, hypothetically, if I gave you a problem and I said use substitution and one of the variables was not already by itself, you would do a little bit of pre-work, so to speak. But I won't ever give that to you because in the real world, no one's going to say you have to use substitution or you have to use elimination. You're a grown-up, you can choose when to use it, whichever you feel comfortable with. And I usually find that a lot of people actually prefer elimination regardless by the end. So yeah, it's kind of a spoiler, but not too much. So step one, already done. We boxed it in. Our y was already by itself in the second equation. So I'm going to go on to step two, which Jordan, you already kind of hit on there, which is to substitute everything from that box into the appropriate variable. Now this time the box is representing my y. So I'm going to rewrite this top equation, 10x minus 2y equals 7. But when I get to that y, that's where the substitution takes place. Careful, it'd be 10x minus 2. Y is the only thing that we pull out. And in its place, wrapped with some parentheses, is going to be the 5x plus 1. I don't want to lose the 2 from that top equation. It's still there, as is the equal 7 after the parentheses. So again, pretending that we don't know this is a special case, we just did step 2, we wrapped it in parentheses. Step 3 is to solve the new equation we've created for the remaining variable. Looks like we're solving for x. So again, just pretending like this is a regular problem. Set up my guideline. Where are your eyes drawn to next? Those parentheses. And for the parentheses, what are you going to do? Distribute, not just any 2, a negative 2. Giving Marissa her credit. Distribute, she's right on it. The 10x though, we didn't touch, so we bring it down. The negative 2 times 5x is going to give me a negative 10x. The negative 2 times 1 is going to give me a negative 2. Bring down my equal, bring down my 7. With parentheses out of the way, what do we usually check for next? Like terms. Do we have like terms here?
Yes.
Yes.
Sure. What are they? 10x and negative 10x. Now, if you combine them as is, what happens?
They cancel out.
They cancel out. You get 0x or just 0. And for our purposes, 0 usually disappears. So these like terms, we didn't know it was going to happen, but these like terms got rid of all of our variables. What's left?
2 different numbers.
2 different numbers, and not just any 2 different numbers, 2 different numbers that are claiming to be equal.
And this is indicative of how we would know after going through this that we have a no solution because negative 2 is not equal to 7.
So good, you summarized it very nicely for me. Negative 2 obviously does not equal 7. The only numbers that equal, well, the number equals itself. So negative 2 does not equal 7. So how would you describe this statement? Well, yes, I know we know it's going to be no solution, but if we didn't know no solution was a thing, would you say this statement is true or false?
False.
When you reach a false statement, only then do you know that you have no solution. Oh gosh, sorry. Spaz. Now we pretended we didn't know what was going to happen here. We pretended like we were just treating this like any old problem. But what happened was, as soon as all the variables disappear, do you have anything left to actually solve for? No, because we're always solving for a variable. Well, if they're all gone, well, now we need to adjust and say, what's left over? And in this case, what was left over didn't make sense. It was false. -2 does not equal 7. And if I tried to adjust this, some people would say, well, what if you add 2 to both sides? Great, you get 0 equals 9. Is that any better?
No.
No. If I try to subtract 7 from both sides, I'd get -9 equals 0. Is that better?
No.
No. No matter what you try to do, keeping in mind the equal sign is going to force you to do the same thing on both sides, you're always going to have a false statement. So as soon as the variables disappear, I always recommend look at what's left over. Don't try to do anything else because there's nothing else you can really do. So then there's infinitely many solutions. Let's pretend we didn't know that. We're going to pretend it's just another system of equations. And we're going to solve it with substitution. So get one of the variables from one of the equations by itself if necessary. Thoughts?
I honestly find these equations like a little confusing. I don't know why, but it's hard for me to understand them.
Do you see any variables up there that are on either the left side or the right side of the equation with nothing else?
Could I ask a question?
Yes, Amy.
Wouldn't you always do the y equals -3x minus 7 to plug in for the y?
Well, I can't say will you always, because if we went back to our problem earlier, we had x equals. So I can't say that it'll always be y by itself. I can't also say that it'll always be x by itself. It really is going to depend on the problem. So in this case, yes, and I assume, Toby, you said you saw a variable by itself. Was it the y in the top equation? So you're seeing it. We just need to work on then saying, okay, this is what I see, therefore this is what I do. So you're telling me that the y in the top equation is already by itself. Well, according to step 1, that's what I wanted. So I'm going to box in what it is set equal to. So Toby, what is that y set equal to? -3x minus 7, the whole thing. So I'm going to box in the whole thing. That's step 1. Step 2, substitute everything from the box, which is right there, into the appropriate variable of the other equation. What do you think the appropriate variable is for that box?
The y, because the y is by itself on the top equation. So you would just plug it in for y.
So the y is the one by itself. The y is equal to our box. So anywhere we see a y now, we can replace it completely with -3x minus 7. And the only other place we see a y is in the second equation. So I'm going to rewrite the second equation.
So, oh, never mind. Okay.
Go ahead, give it a shot. What's the second equation look like? Let's start from the beginning.
I went from, I was looking at the first equation, because I'm like, then how did 5x plug into 2y? And then I noticed it's just the same thing. Because in the first one, the solution, it was y equals 5x plus 1, and then you plug that into 2y.
Right. Well, careful. I'm going to nitpick real quick. I didn't plug it into 2y. I just plugged it in for the y.
Yeah.
Which is why down here, we still had a -2y. The y just looked a little different. It was 5x plus 1.
Yeah, I made it back finally.
He told me I had to find you.
Yeah, he said he was gonna send you out to me. I was like, no, I had a bad week.
No.
So-
I have more tennis today, so I can chase after all the students that I've lost.
I'm an ex-smoker, so I don't run. It would have been that hard.
So Amy, I know you know where this is going, and I hate to stomp on your excitement. But I want Toby to talk me through this real quick, just so maybe we can get him to that same level of comfort. So Toby,
Yes.
our y, according to this one, is -3x minus 7. So that's telling us anywhere we see a y, we can replace it with exactly that. So if you were going to walk me through the process of writing this second equation again, why don't you start me from the beginning? What would you begin writing?
-9x
Okay. negative 9x
minus 3,
minus 3.
and then you would plug in parentheses after 3.
So the y's gone.
Yes.
In its place with parentheses, you said.
Yes, and then you put in negative 3x minus 7.
Perfect.
Then you close it.
Because that is my y now, right?
Yes.
Okay.
And then equals 21.
Spot on. So far, so good. So that was step 2. And you already used the hint. You wrapped it in parentheses nicely. So step 3 is we're going to solve this new equation we just created. So I'm going to set in my little guideline like usual.
And then
So now what's your gut telling you, Toby?
you distribute the negative 3 into the parentheses.
Distribute the negative 3 into parentheses. So this first negative 9x is still there. Negative 3 times negative 3x is positive 9x. And negative 3 times negative 7 is going to give me a positive 21. Bring down everything else I didn't use. So far, Toby, I'm right there in agreement with you.
Well, for like terms,
Look for like terms next. Do you see any?
yes,
What do you see?
negative 9x and 9x.
Negative 9x, positive 9x. And what are those like terms? What happens when you combine them?
They cancel out.
They cancel out because negative 9 plus 9 is 0. And zeros vanish. Well, then I think, uh-oh, this is kind of weird. All my variables are now gone. So I take a step back and I look at what's left. What's left, Toby?
21 equals
21 equals 21. How would you describe that statement, Toby?
It's equal.
It is equal, therefore it must be true. 21 will always equal 21. Well, guess what a true statement means? It has infinitely many solutions. So to bring it full circle, to summarize, oh, sorry, Marissa has a question. Are the parentheses for the y what you're bringing down? I couldn't hear Toby very well. So yes, if I were to highlight it here real quick, let's go something bright. This right here is my y, which goes right there. That's the only thing being swapped out. Did that answer your question, Marissa? Okay, yep. So all we're doing was doing a quick swap. Everything else around it stayed put. Pull out the variable that we're replacing. In its place, whatever we're putting in there, we wrap it with parentheses and we go. Yes, Jordan.
Just trying to make sure I'm keeping good notes here.
Mhm.
So we would say that when presented with no variables in a false statement, you have no solution. When presented with no variables in a true statement, you have an infinite solution.
So,
Better to write his notes. 'Cause I
I'm not
noticed
sure if they-
in both statements, the variable went bye-bye, but one's true and one's false.
good. So yes, when the variable disappears altogether through the process of solving it, no fault of your own, it just happens. You know you're in the special case. To determine which of the two special cases you're in, yes, you look at what's left over. If it is a false statement, it's no solution. If what's left produces a true statement, then it's infinitely many. Now remember, these are special cases. Most of the time, when you go through these steps, you'll actually be able to see them beyond step 3. Because if you think about it, we only made it to step 3 on this process before the variables disappeared altogether. If it is just an average or just a regular system of equations, you'll see it all the way through. You'll get an x, you'll get a y, piece them together as an ordered pair. So this problem here that we did originally is going to be the majority of your problems. But in the event your variable disappears, not because you accidentally forgot it, but because the process made it happen, look at what's left over. If it's true, it's infinitely many. If it's false, then there's no solution. Good. It's a good summary. That's a good way to end our notes on for today.